Now we want to address interference and interference-related phenomena. And one of the more striking areas that interference plays a role, at least in everyday circumstances, are places like soap bubbles. And when you look at a soap bubble very, very closely, if you can perhaps capture a soap bubble on a bubble wand or something like that, and look at it, especially if you can see a light source through it. So, like, hold it between you and a light source and observe the patterns and colors in the bubble's textures, the texture of its surface. Um, this is not because the bubble or the soap itself is colored, although the soap itself may have some dye in it. But the colors that you see in soap bubbles are actually due to the soap bubbles being a very thin film and the way that the light interacts with that film. This is also why oil spilled on the ground, very thin layers of oil that might fall on, for example, asphalt or concrete, can have different colors through them when you're looking at it. So this is all due to the idea of interference. And interference is a form of optics known as physical optics. So here we're actually taking the wave nature of the light into account when we do physical optics. And one of the most striking areas of interference at its root is when light waves, or they're not restricted to light. It can be any wave. This is a water wave. But anytime light waves cross paths, okay, when light waves cross paths, or any wave cross paths, um, a few different things are possible. If the light waves add up or meet such that their crests and troughs are at the same spot, peaks and valleys, then you will get what's called constructive interference, and the light waves will reinforce each other. And if you get where the peaks and valleys meet together, so a peak from one wave meets a valley from another wave, then you get what's called destructive interference. And you won't see any signal. So the classic example in water is if I have two sources of disturbances in the water, say right here and say right here. In that case, when the disturbances in the water flow outward, water typically will move in spherical or circular patterns. They're really circular, they're surface waves. And so these circular patterns spread out, and each one of these is going to create a circular pattern. And so where these circular patterns overlap, right here, 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 and so on, these are points where constructive interference is happening. These are points where the crests of one wave and the crests of another wave are meeting each other, and you get constructive interference. Notice, okay, that there's a line, this central line right here, connecting these points. This line is directly halfway between the two sources. So you will always get a region of interference that is halfway between your two sources, especially when your initial signal is the same for both waves. So both of these waves would have the same amplitude, in other words. And we're also going to assume that they started at the same time, right? So how would we do this with water waves? So when you do this with water waves, one way you can do this is create a wave in a tub or a uh, an aquarium or some kind of case like that, and just disturb the water in some fashion, but then put a barrier in the middle of the tank. But and let me do it this way. But put a barrier in the middle of the tank, and as a matter of fact, put slits in that barrier. So as the wave is coming here toward the barrier, some of the water makes it through the slits here, and when the water hits those slits, it will actually form these circular patterns. So how can we do this with light? So this is what's known as double slit interference. Okay, so this is double slit interference. And I guess I should say, notice what happens here is that if I were to draw, okay, um, the patterns here that I would find, there would be as this point propagated out toward here and this point propagated out toward here, I would find a region where if I were to put a screen right here, imagine this is a screen, and this screen measured the intensity of the water waves, there would be a strong intensity right along this central axis. There would be a strong intensity right here. There would be a strong intensity right here. And in between, there would be nothing. There would be dead space. And this is where your destructive interference is happening. And so the basic idea of interference is that you get this pattern of high intensity, nothing, high intensity, nothing. And if I were to stretch this out, I would get another region of high intensity out here, and there would be a region of high intensity out here. But the intensity would get smaller the further I go out. Even though I would still get regions of higher intensity, they would get smaller the further I moved out. So your central, what we call the central maximum, is always going to be your highest intensity. This is where the bulk of the water waves are going to meet, and then where other constructive interferences happen as they spread out. You will then notice that you'll both get regions of nothing, where your destructive interference happens, and you will get your other regions of constructive interference are going to get smaller in intensity as you move away. And so this is endemic of interference. This is what waves do when they interact with each other. And so in the turn of the 1800s, we applied this principle to light. And so what we did was we took a monochromatic light source, and in fact, his name was Young. This is known as Young's double-slit experiment. And in the early 1800s, he took a monochromatic light source. I forget exactly what he said. It might have been a sodium lamp of some kind. But you take a sodium lamp and you send that light through an initial slit, which helps kind of collimate the light. And then you send it through two small slits. And those two small slits then produce an interference pattern on a screen, some distance, capital D away. And so, if you were to do this particular experiment, you would notice that you would get interference in packets. So you would get a central interference packet where you would get regions of light and dark, and then you would see a really dark maximum on either side. And then you would get another small packet of interference on either side of that, and then another dark patch of interference, and then another small region of interference, and so on. And so this particular pattern is a rather complex interference pattern, but this is what you would see. And the wider you make your slits, okay, the more like this pattern you're going to see. Now, modern day, what we would do is instead of using just some sort of monochromatic light source and sending it through a single slit first, what we would do is use a laser and then just let the laser beam hit these two slits. Use slits that are so small that the laser beam's width hits both slits, and you then get an interference pattern on the screen. And so what's happening is the points of bright light on this screen are going to be where the two waves coming out of the slits, one wave coming out of the slit this way and the other wave coming out of the slit this way, or the wave coming out of the slit this way and a wave coming out of the slit this way, when those two waves constructively interfere, so when one wave has this pattern and the other wave has a pattern such that the crests and troughs line up, then the result is that you get a larger wave. You get constructive interference. Those are the bright spots on the screen. When the waves reach the screen out of phase, such that the waves and troughs on one wave cancel out with the waves and troughs on the other wave, then the result will be destructive interference and you don't see anything, right? So when you do this with a, like I said, with perhaps a laser experiment, what you see is when the laser beam is wide enough to encompass both of the slits, this is what you would see. The laser beam hits both slits, and what happens, just like the water, when the water comes in and the water hits both of those slits, it starts to work like a spherical wave. This is the crucial point here. The waves of light do the same thing. And so when the waves of light hit these two small slits, they move from being plane waves to becoming spherical waves. And this is due to Huygens principle. So Huygens principle says that each point along a wavefront of a light wave is capable of acting like a spherical wave. It's capable of being a point source for a spherical wave. And when the light that makes it through the slits, pardon me, the light that makes it through the slits act as those point sources. And so then, because this is now a point source of a spherical wave, the light spreads out. And because the light spreads out, both of the waves the light spreads out, they will overlap. And where they overlap, you will either get constructive interference if the waves add up, and you'll get so constructive interference would be the bright dots in here, and they're right here, and so on. And then the destructive interference would be where you see the dark lines in here, and here's a major a line of destructive interference. Here's a major line of destructive interference. But even in this brighter region right in the middle, you still have lots of individual lines of constructive and destructive interference. So what is the math? How does the math work with this? So constructive interference happens when a light wave from the first slit and the wave from the second slit match up such that when they reach this point, their waves are in phase with each other. And actually, that's not a terribly great representation of that. Let me draw that a little bit better. So their peaks line up, their troughs line up, and their peaks line up, and so on. So when they reach this point such that they're in phase at that point, okay, they don't necessarily have to be in phase throughout the rest of the trip. They don't necessarily have to. They just have to reach this same point such that they're in phase. Then we're going to get constructive interference, right? Then we're going to get constructive interference. So what this means is whatever the path length is, this R1, and whatever the path length is for R2, the difference between these two paths, and in fact, since R2 here is larger than R1, let me write it like this. The path length between these two paths would have to be such that the absolute difference between R2 and R1 has to equal a wavelength. But not just a wavelength, but it has to equal an integer multiple of a wavelength. Okay? So for constructive interference, we're going to get constructive interference when the difference between these two paths is equal to an integer multiple of a wavelength, because when that happens, the two waves will in fact be in phase when they reach this point. So m is just an integer. And it can be 0, plus or minus 1, plus or minus 2, plus or minus 3, etc. And the reason these are plus or minuses and the reason I used absolute values here are because the same story would hold for a point down here, right? These two distances are going to be different. And in this case, R1 is going to be longer than R2. And in the original case, R2 was longer than R1. But the absolute value between their distances is what matters. And when I go on one side of this equilibrium position here, we call this plus m, and this would be minus m. Okay. So it's just basically kind of saying, okay, I'm going to define this central axis midway between the slits at the screen. I'm going to define that as a y position of 0, and then I'm going to increase my y in the up direction. I'm going to decrease y in the negative direction, and the m integers then get plus and minuses associated with that. So how can I find what this distance is? That's the focus of the next part, right? So if I look at two rays coming from one of the first slit and the second slit, the distance between the two slits is a lowercase d, okay? So d is distance between slits. And theta is the angle that this point, I'm assuming this is a constructively interfering point. Theta is the angle that point P, a line from the center of the slits to point P, makes with the central axis. Okay, so this dotted line here would be the central axis. And we're going to assume, okay, that this screen, this distance D, the screen distance capital D, is much larger than the slit distance D. Okay, so we're assuming that the distance to the screen is much larger than the distance between the slits. And in that assumption, if that holds true, then both of these rays, S1 and S2, are going to be very close to the same angle with respect to the plane of the slits. So what we mean by that is this angle is also going to be very approximately theta, and this angle is also going to be very approximately theta, okay, under the assumption that this holds. So the line from S1 to P is coming out at an angle theta, and the line from S2 to P is coming out from at an angle theta. So these two lines are nearly parallel. Okay, they're nearly parallel. And what that means is the distance between, or the difference between their lengths, this distance R2 minus R1, is going to be equal to this extra distance that R2 has to travel, right? So the distance difference between their two lengths is going to be that extra distance that R2 has to travel. And so we label this distance as delta L, and this equals that R2 minus R1 quantity. And then from the geometry, we can see what happens. The length of the slits is a distance d, and this line makes a right angle with R2, so that's a right angle and that's a right angle. And it turns out, we're not going to prove it here, but you can prove it to yourself that this angle theta must also then be this angle theta. It's a short exercise. You can prove it using similar triangles. And since this is theta, this is d, this length here is what we're after. So what we have is delta L is equal to d sine theta. Okay, but we wanted that difference in length to be equal to an integer multiple of the wavelength. And so the condition for constructive interference is that d sine theta equals m lambda. This is for double-slit and let me write that. My penmanship isn't always the best. So this is double-slit constructive interference. Okay. And under that condition, we can calculate where the maximas ought to be. Now notice there should be a central maximum right here, halfway between the two slits, and that makes an angle of 0 with the central axis. So when m is 0, this is the m equals 0 maximum. When m equals 0, sine theta would be 0, but that holds because since the angle is 0, the sine of 0 is 0, and so both sides of that equation would be 0 equals 0. And if I do this experiment with a very wide beam of laser, then this is actually very close to the pattern that I would achieve here in my laboratory. And as a result, okay, so what you see is your brightest constructive interference at your central maximum. And then either side, these are the, so this is the m equals 0 maximum. These are the m minus 1. This is the m plus 1. And this would be m minus 2. This is the m plus 2. And these are equals. I should put equal sign in there. And your destructive interference, okay, is going to be when your waves reach out of phase. And so what that means is out of phase means that d sine lambda or d sine theta is going to be equal to m times half of a wavelength. And so what we essentially at the end of the day want is m plus 1/2 times lambda. Okay, so when I arrive such that I reach out of phase by half of a wavelength, then I get destructive interference, and these are these points right here. Right now, a couple other things to note. So we define the distance that a maximum appears on the screen to be a distance y. So y is equal to distance on screen from the central maximum distance of a maximum from the central maximum. And so with that in mind, we can use a very nice approximation to do some calculations. So under the assumption, under the assumption that these slits are very narrow and that the distance to the screen D is very large. Okay. Under those assumptions, then these angles, I should say, these angles, theta 1 and theta 2, are going to be very small. Okay. So here's the central axis, and the angle to the first maximum might be here, and the angle to the next maximum might be here. And whoops, I want to label this capital D. And this would be distance D. From this would be theta 1, this is theta 2. So this is m equals 1, or 0. This is m equals 1. This is m equals 2. We have d times sine theta is equal to, this is y1, and this is y2, right, is equal to m lambda. The sine theta we can simplify a little bit because the sine of theta is equal to y over d. So for a given scenario, d times y over d is going to be equal to m lambda. Okay, so, and that's just using the ratio of, or the definition of sine, if you will, right? And so let's do an example using calculations. And so what we're going to do is suppose we have laser light and we're shining it through two slits, and we shine that light on a screen. Here's our central maximum, or a central axis rather. And so let's say that lambda is 632.8 nanometers, which is typical of red laser light. And let's say that D, the distance between the slits in the screen, let's say D is 1 meter. And let's let the distance between the two slits is equal to, say, let's say 1/10 of a millimeter. So D is going to be 0.1 millimeters. Okay. So here are my questions. Where are Y0 going to be? Y1, Y2, and so these are going to be the positions of our maximas, okay, our constructive interference. And I want to know, just for kicks, where is the first minimum going to be? Okay, where's the first minimum going to be? And so now the first one isn't going to take any work because this is always going to be at a y of 0. Okay, so the central maximum will always be at a y of 0. So this is your m equals 0 maximum, and that will always be along the central axis. So it doesn't have any displacement. But where will y1 be? So we have d times y1 over L, or y1 over d, is going to be equal to, and these subscripts are the m letters, right? So this is going to be equal to 1 times lambda. So y1 is going to be equal to lambda d over d, and this is going to hold ubiquitously. This formula is going to hold. And in fact, let me throw the m in here, just because we can use this formula again and again, right? So in the first case, y1, this is going to be 1 times 632.8 times 10 to the negative 9 meters divided by 1 times 10 to the negative 4 meters. Okay? And when I do this, I'm going to get, so 632.8 times 10 to the negative 9, divide that by 1 times 10 to the negative 4, and I get 6.328 times 10 to the negative 3. Okay? So 6 millimeters. The first maximum, the y equals 1 maximum, right here, this will be 6.328 millimeters. Okay, so very small. These are very, very small in width in most cases, especially the longer your wavelength. These are going to be very, very small. So if this were my situation, then I would measure the distance between here and here. And let me, in fact, change that color. This distance between here and here would be 6.328 millimeters. Okay. So what about the next distance? Well, we can use the same formula. Y2 would be m equals 2 times 6, 638 632.8 times 10 to the negative 9. And technically, this is multiplied by 1.0. I really should have put that in there. Divided by 1 times 10 to the negative 4. And so when we do this, right, we're essentially going to get twice as far. So we would get 12.6 millimeters. Okay. Now, in truth, okay, you can see that these are in fact not necessarily. Now, the first two here look like they're about twice as far away. But as you move out, the distances between them seem to get a little bit smaller. Okay. In truth, this is what's actually going to happen. So here in this formula, if this were completely accurate, it would be linear. Whatever my m was, it would just the next successive y would just go by that amount. The next point of constructive interference would go up by that amount. But what actually is happening is this approximation allowed us to make this approximation that this distance right here is equal to d sine theta. So in fact, d sine theta is a slight approximation. If you actually work out the triangles in this graph and work them out in detail, it actually is a pretty convoluted set of triangles to get the lengths R1 and R2 using the law of cosines. And then the different you find the lengths and then you take the differences between them and so on. And so that's the more rigorous way to do it, and that actually determines what's the distance between those constructive interference points. But as long as this approximation holds, then this approximation is pretty good. It's not necessarily exact, but it's pretty good, especially for your low order m's. And so as a result, we take that to be good enough for situations like this. Now, what about my destructive interference? Let's find out where that point is. And so let's throw in a new slide here. And we're going to get d sine theta is equal to m plus 1/2 times lambda. And so this is again d times y over d is equal to m plus 1/2 lambda. And so this y now is going to be our point of destructive interference because we're looking at half wavelength multiples. Okay, so the first minima, this large black space right in here and right in here, right? So this large black space here and this large black space here correlate to the m equals 1/2. Technically, it's the m equals 0, but it's where but it's when m plus 1/2 equals 1/2. It's the first destructive interference part. So as a result, y is going to equal 1/2 of a wavelength, because m is 0 at this point. So this is going to be 1/2 lambda times capital D divided by d, little d. And so this is effectively lambda d over 2d. And so this is basically effectively dividing our previous result by 2. So I need to divide that result by 2, 6.328 millimeters. And if I do that, I get 3.16 millimeters. And so that means the first region of destructive interference is going to be at 3.16 millimeters. Okay. And you can crank out, any value for the constructive interference and the destructive interference you want. As you get further out, the results will agree less and less, and that's because of the d sine theta is that approximation. But in any case, especially for low order interference pattern, it is going to be a pretty good approximation. So that is the double slit interference, and in the next set of videos we will look at thin film interference and single slit diffraction. So stay tuned.